Greetings, Matt Roscoe here at the University of Montana, and a lecture on section 3.5 from our text, Derivatives of Trigonometric Functions, for our course Math 570 Calculus for Middle School Teachers. Well, I want to talk a little bit about the derivative of the sine function, and then we'll go and see if once we develop some good strong intuition about what that derivative is, we'll find the derivative of the cosine function using the sine function. And once we have the sine and the cosine, we'll use that to find a derivative of the tangent function and then work through a few examples. So let's use the Desmos link below to make a conjecture about the derivative of the sine function by inspecting the graph of the sine function. So we'll go ahead and go to Desmos now and take a look at what we have here. We have a point on a sine wave. One thing I want to make clear is that all of these rules assume that we're working in radian measure, and that's perhaps a reason why if you do teach this idea of there's two different ways to measure angle, radian and degree. One of the reasons we teach radian measures because all of the derivative formulas in calculus depend on the angle arguments being in radians. So we're in radians. You can see that we have a sine wave that has a period of about 2 pi, or a half period of about pi. And we've got a point on that graph. Let's slow it down now. And take a look at what happens when we plot the tangent to the curve at that point. So the tangent to the curve, we can see cycles between negative, 0, positively valued, 0, negatively valued, 0, positively valued. So it seems like, just like the curve itself, that the tangent to the curve is cycling between negative and positive extremes and passing through 0 at regular points along its way. So one thing we could notice is that somewhere right in here we're near 0. So we would expect there to be a point below here at 0. Of course, that would be the case here as well. We're near 0 in our slope, and here as well. So it's certainly, the derivative is certainly not itself, because the derivative, it would be valued at 0 at these points. So let's put a point in there and watch it. I don't like that color. I'm going to make it black and watch it as it cycles, so we can see that now we're steeply negative, we're growing positive, 0, steeply positive, decreasing to 0, decreasing to negative, and increasing to 0, and so on. So if we go ahead and think about what is that function that black dot is tracing out, well, it's going to look something like that. Again, I don't like that color. I'm going to make it black. And we can see that the derivative of the function looks a heck of a lot like the function itself. It's cyclic. It oscillates between values of -1 and 1, passing through 0 at the peaks and valleys of the red function. And so you might think to yourself, well, that looks like another trigonometric function, and indeed it is. And hopefully you've got some intuition at this point about which trig function is. If you were all here with me live, I'd take some guesses, and I'm sure that one of the guesses I would get is that this is the cosine function. And let's go ahead and plot the cosine function and put it in a color so that we can really see it, green. And let's go to projector mode 2 so we can really see what's going on. And indeed, that green function is the graph of the derivative of the red function. And so what we've shown here, or at least provided some strong evidence of, is that the derivative of the sine is the cosine. We're going to accept that as truth. Certainly this isn't proof of the assertion, and if you'd like a formal proof, that's available in the back of the text in the revisitation of theory. This is a fairly hard thing to prove in mathematics and requires a good deal of argumentation, but I encourage you to look at it if you're curious about the formal proof of the derivative of the sine as the cosine. Okay, well, let's go ahead and run back to our page. And certainly, this is again not a proof, but we have strong evidence that the derivative of the sine is the cosine. Now the question becomes, how can we use that to find a derivative of the cosine? It turns out that the derivative of the cosine is negative, the opposite of the sine. So let's see if we can somehow use this fact to think about what's going on. Okay, so I need to escape out of here and get my Elmo cam up and running. Okay, there. So where do we begin? Well, we know that the derivative of the sine of x is equal to the cosine of x. And what we're trying to show is that the derivative of the cosine of x is equal to something. And we're going to try to employ, I guess, this result in finding the derivative of the cosine. Well, right away you should think to yourself, wait a minute, I think that the cosine can be written as a sine. So let's go back to Desmos and take a look at how we can rewrite the cosine in terms of the sine. So if I go ahead and type in g of x equals cosine of x, well, that's the cosine of x. And the question is can you make that curve using a sine argument? So h of x equals a sine of x, and it looks like what you're going to need to do is you're going to need to move that blue curve. You're going to have to shift it to the right. And those of you who've taught transformation know that that means subtracting some k value from the x value. So if I subtract a k value, I can move that blue curve back and forth. And the question is what amount should I move it? Let's see. So when it's valued at 0, we're right there. If I subtract a negative 1.4, 1.5, that's right, it's somewhere in the neighborhood of pi, isn't it? So let's do that. Let's step it by pi. Let's let k run from negative 2 pi to 2 pi by pi. Let's see, did that work? No, it didn't. Negative 2 times pi to 2 times pi. Doesn't seem to like my use of pi. But let's go ahead and assume then that where we're at right there is at negative pi over 2. So if we subtract a negative pi over 2, we can write any cosine curve as sine x plus pi over 2. So hopefully that reviews this little step right here. Oh, erase all. So we can rewrite a cosine curve as sine of x plus pi over 2. And now we know the derivative of the sine, but it has an argument inside of it. So what we have here is we have an application of the chain rule. So what we would do is take the derivative of the outside and then multiply it by the derivative of the inside. Well, the derivative of the outside would be the cosine of x plus pi over 2 times the derivative of the inside, the derivative of x plus pi over 2. Well, pi over 2 is a constant, and the derivative of x is just 1. So what we get as a derivative of the cosine of x is just the cosine of x plus pi over 2. Well, that's kind of an interesting question then. What does that graph look like? So let's go back to Desmos and take a look at what, we'll go ahead and add pi divided by 2 to this. We'll go ahead and get rid of these two and ask ourselves, well, what is that thing? So the cosine of x plus pi over 2. And what it appears to be is something similar to a sine curve. So h of x equal to sine of x. The reason I say that is because it starts at the origin, but it's been reflected about the x-axis right? So the purple curve is the sine of x, the red curve is our derivative, and we're trying to figure out how to write that. And it turns out the right thing to do to reflect it across an x-axis is to give it a negative in front of it. And so indeed the derivative, which we wrote as cosine x plus pi over 2, is equal to the negative of sine over x. And we can conclude that that's the derivative of the cosine. So the derivative of the cosine is negative the sine of x. Okay, one last one. Let's take a look at this. How can we use sine and cosine to find an expression for the tangent, the derivative for the tangent? So let's go and attempt to try to construct a derivative for the tangent. So the derivative of the tangent of x. Well, if you remember a little bit from trig, or if you'll go back and review, you'll find that the tangent's the same as the ratio of the sine to the cosine of x. And so what we have here is a quotient rule. We have a function on top and a function on bottom in a division statement, so we can apply the quotient rule. We know the derivatives of both of these, so it's the bottom times the derivative of the top, so it's cosine of x times the derivative of the sine, which is the cosine of x. Bottom times the derivative of the top, minus the top, the sine of x, times the derivative of the cosine. The derivative of the cosine, of course, is the negative sine of x. And that's all over the bottom squared, so the cosine of x quantity squared. Now we need to clean up. So on top we have a cosine of x quantity squared, minus minus, so it'll be plus the sine of x quantity squared all over the cosine of x quantity squared. One thing you might remember is there is a trig identity that says whenever I have a sine ratio and I add it to the cosine ratio for the same argument when there's being squared, what you get there is a 1. That is called the Pythagorean identity, and it flows from the Pythagorean theorem actually. And so we would rewrite this as 1 over the cosine of x squared, which often is written just for simplifying reasons, fewer brackets, the cosine squared of x. So there we have it. The derivative of the tangent's 1 over the cosine squared of x. Let's do a few examples. So let's find the derivative of 2 sine 3x and see what we get. So let's see, f prime of x is going to be the derivative with respect to x of 2 sine 3x. Constant multiplier comes out in front, and we have the derivative with respect to x of sine of 3x. Here we notice that we have something where we're in the form f of g of x. So a function within a function, that's a classic chain rule setting, composition of two functions. So what we'll get there is the derivative of the outside, the derivative of the sine is the cosine of 3x, times the derivative of the inside, so this would be f prime of g of x, and times the derivative of the inside, which is just a 3, so that is just our g prime of x. Classic chain rule. We can simplify this by calling it 6 cosine of 3x. Might be kind of fun just to look at this one. So if we go to Desmos, let's go ahead and write these into Desmos. So we think that this function 2 sine 3x has a derivative equal to 6 cosine of 3x, And let's take a look and see what this thing looks like. So kind of interesting to think about as I move along this curve, this red curve, I would expect that there would be a zero slope on its derivative at that point, and indeed it looks like there is. I would also expect the curve to reach its highest positive value right here, and indeed it seems like the purple curve is quite high and positive. Let's go to projector mode. This might help a little. So one way we could check this is by just saying, well, what is the derivative d by dx of g of x, and just have Desmos plotted. And there it is in orange. So if I hide and show, it appears to overlay the algebraic derivative that we found. So I think that's pretty strong evidence that we did indeed find the right derivative. Let's try a different one. G of x equals the square root of 1 minus cosine of x. Okay, probably easier to write this as 1 minus the cosine of x raised to the 1/2. Then what we can do is try a chain rule. So this is a function inside of a function. So we take the derivative of the outside, which is 1/2 1 minus the cosine of x to the negative 1/2 times the derivative of the inside. Now the derivative of 1 is just 0, and the derivative of, well, the negative in front of the cosine can be thought of as a -1 coefficient. So we have 1 minus 1 times the derivative of the cosine is negative the sine of x. Okay, so how does that work out? Let's see. We have 1 over 2. This is a square root in the denominator, so we could have this written as 2 square roots 1 minus cosine of x. And in the numerator, what we have is 0 minus a -1 times a negative sign, so that would be a positive sine of x in the numerator. And this would be the derivative for that particular function. Okay, one more. You might want to check that one again on Desmos to graph those two to see for sure. And one more we'll try here, having to do with the tangent. What if we had this function, the derivative of h of x equals the tangent of e to the x. Ooh, this is an interesting one. Okay, so again, you should recognize that this is a function within a function. It's f of g of x. So if we think of it that way, then its derivative by the chain rule will have to be equal to f prime of g of x, right, times g prime of x. So let's go after that one. So first we take the derivative of the tangent, the outside function, and that's 1 over the cosine of the argument e to the x. That's the first piece. And then we multiply by the derivative of the argument that's in the cosine here. So the g of x is e to the x, and its derivative is just e to the x. So e to the x over, oh, I'm sorry, it should be cosine squared. 1 over the cosine squared of e to the x. And I believe that's the derivative for that one. Again, a quick graphical check in Desmos would be worth the effort. Okay, well that's about all I wanted to show you about derivatives of trigonometric functions. Let me know if you have questions, and good luck on your homework problems.